organizing this conference, which has been very interesting until now. I hope I won't be able to stay. And to my apologies, there's a slight change in the abstract in that I will not speak about Hans-Georg Weinberger's framework. So if you'd like, you can get back to that at the end. And I'm not sure about the background of the audience, both in terms of mathematical background and of theoretical background. So I hope there'll be something non-trivial for everyone. And I'm sorry for reading from paper about trust, not English, all my time management skills. So the questions that interest me is the questions of how does mathematical knowledge come into being? What is mathematical knowledge? What's the ontological status of mathematical objects? And how does new mathematical knowledge emerges? And since the 1970s, sociologists and philosophers of science have been calling for empirical study of research-level mathematical practice. David Bloor, Donald Mackenzie, Bruno Latour, Andrew Pickering, many others have called for such studies and provided a theoretical framework that enables following mathematics in action. But in spite of the alleged theoretical possibility and the professed need for such studies, the literature still today contains mainly laments on the lack of such endeavors. And this is something that I found almost in every paper. It has to start with lament on the status of the field. So, except for a few very recent and interesting stuff, some of which represented here, there's very few. In the study parts of which I wish to present here today, I'm trying to perform a sort of laboratory study of, or a theoretical study of a very restricted field, and to give a full description of the events and understand the meanings that participants find in it, without pre-assuming social or natural categories. Due to the practical difficulty in following laboratory work, namely the lack of laboratories, the research was based mostly on in-depth interviews with mathematicians and on the text analysis of many, many drafts along the process. It was along the period of the years 2000 to 2010. What I'd like to do today is tell a story of the emergence of a certain mathematical object in the field of asymptotic geometric analysis. I'll start with a brief presentation of the conceptual tools that we'll be using, then give a short historical mathematical introduction, and then dive into the minute details of the creation and stabilization of a new duality transform for a class of convex functions. My study takes as a starting point the ontological framework suggested by Latour and the after-network theory. According to this view, reality is not made exclusively out of natural elements, which are then interpreted by the human mind, nor is it made of a pre-existing society, which creates the natural world. Rather, the distinction between nature and society is considered the result of the scientific effort itself. In this way, this approach locates itself outside the realist constructivist controversy. As Latour put it, it's real because it is constructive. The basic element, ontological element for after-network theory, is a network which is made out of actants, that is, actors that are not necessarily human. This socio-technical web is constantly forming and reforming the actants which have no immanent characteristics outside the world in the network. Latour also places high importance on the concept of translating, which is also displacing. Scientists move reality from one location to the next, from the wall to the lab, from paper to paper, from nature into words. A chain of translations is formed, in which with each link we give them certain local, material, and particular characteristics to gain mobility, standardization, universality. The ability of an object to move through space and time without changing is very important, and Latour refers to such an object as an immutable mobile. The objectivity and stability of an object is established through the proliferation and strengthening of association with translations. Time many allies to a claim or an object makes it stronger, makes the ties harder to sever, which brings out the quandary of defect builders. builders, that's a quote from Science in Action. Fact builders have to enroll many others so that they participate in the continuing destruction of the fact. But they also have to control each of these people so that they pass the claim along without transforming it, either into some other claim or into someone else's claim. When the translations and ties become so routine that they are hardly visible anymore, the object is black box, and its inner structure no longer exposed. Objectivity is thus the institutionalization of associations. One of the main conclusions of the actor network theory is that in order to understand what science is and how it develops, one should follow its creation in real time. In what follows, I would like to describe the emergence of a new mathematical object as the coming into being through translations and associations of immutable mobile. The mathematical research I've been following belongs to a field developed in recent years, started around 2000, called asymptotic geometric analysis. It is considered a part of functional analysis and deals with finite dimensional objects and their geometric and linear properties as their dimension tends to infinity. It is a rather small research community consisting of between 100 and 200 mathematicians worldwide. Vitaly Milman, here at the board, of course, born in 1939, emigrated from Russia to Israel in 1973. He's a senior professor at Tel Aviv University School of Mathematics, a widely respected mathematician. He's considered one of the founders of the field of asymptotic geometric analysis. Shiri Alston-Avidan, born 1978, finished her PhD cum laude in 2004 under Milman's guidance and has since won various prizes and awards. She is today an associate professor at Tel Aviv University School of Mathematics. The objects dealt with in asymptotic geometric analysis are mainly convex bodies, which are, as their name suggests, bodies that have no inhabitants. AGA considers what happens to various characteristics of convex bodies as we examine them in higher and higher dimensions, tending to infinity. Now, one of the developments in asymptotic geometric analysis that allowed breakthroughs in recent years is the idea of generalizing convex bodies by associating with each body a certain function and considering the class of functions instead of the class of bodies. The next step is translating, and now I'm using translating as their words. The mathematicians use the word translation, although it fits quite well with Latour's use of translation. So the next step is translating concepts and inequalities that talk about convex bodies into concepts and inequalities about functions. They call this the geometrization of this class of functions. Some of the main theorems for convex bodies have already been proven for low-concave functions, and the analysis has been fruitful in both directions. The new insights regarding the class of low-concave functions. The method not only allows solving questions regarding convex bodies, but also gives new insights regarding the class of low-concave functions. This is a subject that Milmans and some of his former students worked a lot on. And one of the concepts that they tried to move from bodies to functions was duality. Now, duality of convex bodies is a long-known concept dating back to at least the beginning of the 20th century. It relates to every body, a dual body, here K, using a certain formula. When Milman and his students tried to translate the idea of duality from bodies to functions, they found a transform based on the famous Legendre transform that allowed them to relate to each function another function, such that the relation between the functions would somehow be equivalent to the duality relation between the convex bodies. But they had a problem justifying that the transform they found, and not some other transform, is the right translation for the concept of duality. Now, if there were a known definition for duality in general, one that you can move around fields of mathematics, that would have been helpful. But duality is a concept that has always been vague in general, and only its manifestations in different areas got a concrete formalization. So it's interesting to open Wikipedia and see the definitions of duality, which are just, here's duality in this field, here's duality in this field, here's duality in this field. But more than that, it's the relation between two objects, usually a symmetric relation, not more. So what they did is they asked around for the main properties expected from the duality concept, and came up with what they named an abstract characterization of duality, the two minimal requirements desired in any duality concept. They then found out that if they look for a transform that will fill both these conditions, only one candidate fits, the one they originally used as a duality for this class of functions. This was especially interesting mathematically, because what they got is a very simple definition for duality, using very few and simple conditions, really trivial. They had defined a concrete transform. The paper written about this was published in Annals of Mathematics, one of the most prestigious journals in mathematics. So now that we have a way of finding a duality transform for a class of functions, we can try and move it around and see if it helps in other classes as well, which is indeed what Millman and Archibald successfully did, and some other mathematicians as well. At this stage, the process of defining duality transform on a class of functions by proving that it is the only transform that satisfies the condition became routine, a legitimate procedure in the field, a tool, perhaps in Reinberger's terms, an epistemic technique. To stabilize and strengthen this concept, Millman and Archibald are working on associating it to other elements, other function classes, other mathematical questions, other mathematicians. Such an opportunity is presented when Millman meets with Bobkov, who is working on duality for heavy-tailed functions. Here's where I got it. Millman, Archibald, and Vidal promise will prove that the transform he's using is the only one satisfying abstract duality in the relevant class of functions, complex Rn. This was to be a simple, non-demanding proof that Archibald and Vidal, pregnant in Israel, was supposed to send by email to Millman there was a problem in the world talking in conferences. But after some efforts did give rise to a proof, Archibald and Vidal started to suspect the theorem is not true. There is actually more than one transform satisfying the abstract duality conditions in this class. And indeed another transform was found. This surprising new actant in the game required a reorganization of the network. It wouldn't let Millman and Archibald and Vidal continue with their original plan of tying Bobkov and heavy-tailed functions to their abstract duality. Instead, they have a few options. In Hans-Georg Reinberger's terms, they have reached a conjuncture. One option is they can abandon the new direction altogether, but that would be losing whatever time and effort was already put into it, plus the connection to Bobkov and heavy-tailed functions. Another option they have is they can see the issue as a sum of problems, their original definition of abstract duality. But obviously this would undermine the work they have already done and published over the last few years. Besides, abstract duality already has at this point some existence in the world, namely in the form of ties to other theorems, objects, and mathematicians, and we can't go down so easily. So I'll skip some other available possibilities and move straight to the actual scenario, which was to see the new transform as a second duality on this class of functions. The published announcement paper was named a new duality transform. This would weaken the strength of their former approach regarding the abstract duality definition, which to some extent relied on it providing a single duality transform for each class. In terms of the relation to Bobkov's work, it gives up the tie to it, but on the other hand does not hurt it. This option takes a certain risk. Its success depends on this new unfamiliar actant, on its stability and durability, namely on its ability to make new ties. Naturally, Archibald and Millman now put efforts into strengthening the new transform and making it into a durable object. First of all, a lot of translations start to take place. The first formula Archibald has is, she says, very ugly. It's composed of two functions and looks cumbersome and uncomfortable to work with. So the first thing Archibald does is to try to find a simpler expression for the function. The new expression allows moving the formula around, entering it into new combinations using it, But on the other hand, it hides the way the formula was created, its details, what it's made of. After a few more transitions, the formula can now be read as a sentence, if described over the phone. But the detailed information that was once expressed by it is now relegated to side notes and remarks. In the final paper, transform appears in more than one form, not only the concise mobile form of it, but also more detailed forms. This fits well with Latour's idea of the fact builder's quandary. In order to enroll others, Archner, Vidan, and Milman leave margins open to negotiation. They allow their object to be taken by others, used, manipulated. But they also have to take care not to make this into someone else's object, so they hurry up and publish their first paper as soon as possible, before considering all the implications this object might have. The fact that Milman is a known figure in his area makes this possible. Another type of translation, which Milman and Archner and Vidan give high importance to, is what they call a geometric interpretation. They start working in this direction almost immediately after first coming across the new transform. Archner and Vidan explains that this would allow them to see what the transform does. As the former mentioned translation allows explaining the transform in one line, this translation allows explaining what it does in simple terms. If you take the epigraph of F, and then take its dual, and then reflect it on the x-axis, this is the epigraph of our new duality transform, here named A of F. They find more than one such interpretation and use each one for different purposes. Again, the interpretation gains in clarity and stability, but closes other options for other interpretations. That is why at this stage there is no decision on one official interpretation, but instead a few different options are presented side by side. Once more we see how the balance is kept between the objects being immutable and making it mobile. Another important type of translation this transform allows is a translation of more notions from the geometrical of convex bodies to functional objects. In other words, the geometrization project. Quoting Milman, actually, the best reaction on these new things was not on the new duality itself, but on the fact that, and that's a conclusion from it, there are new concepts arriving to the class of concave functions, and suddenly it is found out that there is much more structure here. And this caught the attention of people that their opinion means the most to me. Exactly this, people jumped up and said, yes, this is something interesting. Now here you can see exactly how the ties go beyond the separation of internal mathematical considerations and external human ones. The potential ties Milman sees here are to humans and mathematical structures alike. Throughout the time between their first encounter with the transform and the first published paper, the transform's name and sign change a few times. It is first named T, which can be considered a general name for any transform, a good name for a counterexample, but not for an independent object. Later on it becomes A, and in recent past Archner and Vidan told me it now has a name, geometric duality, and that they also plan to change it, the sign, to designate it. Simultaneously with the coming into being of the object, its biography is constructed. Contrary perhaps to common opinion, mathematical papers are not just theory and proof, but the introduction to a mathematical paper may arguably be considered one of the most important parts of it. To expand later. In it, the history of the subject is often mapped out. The story of the result is given here, explaining why it's interesting and worthwhile at all. I think sometimes explaining why a mathematical result is important is more significant than explaining its truth. Again, the subject I can explain. The story of our transform changes along the work process. The first paper presents it as a surprise. The story told is one of the routine, expectations, and then a turn of event. To do that, the private emotional experience of Archner, Vidan, and Milman is transformed into a mathematical objective experience by making the practical routine a mathematical phenomenon. Their work is presented as a natural continuation of their previous work. The new class of functions, suggested by Markov, meant chance, is now presented as a natural extension. But the element of surprise, which can work as a justification in the first announcement paper, and in the small community in which Millman is very well known and respected, cannot work as a justification for this transform's importance for long. Soon Millman and Archinovidan gave up the narrative of surprise in favor of the idea of a hidden structure. The new transform, they say, allows us to unveil the geometric structure of this class of functions. The transform is now interesting because it allows the translation of geometric notions from the class of complex values to the class of log-complete functions. The class itself now becomes interesting because it has this transform, and not the other way around. The class even gets its own new name, G-functions, or geometric, based on the existence of this transform on it. The new duality, starting off as some kind of counterexample, gets the name geometric duality, which implies the significant essential duality. The first duality is now relegated to another role. Not to worry about it, it's the Legendre transform, it would not disappear. It should perhaps be stressed that this is not some cynical game by Archinovidan and Millman. Their change of story reflects the change in how they themselves view the change of events, the chain of events. So I've presented here a few features and aspects of the emergence of a mathematical object. Just some points out of an array of aspects you can describe. And I think we can learn from the following of the new object through its very first steps, how a mathematical object emerges in multiple planes simultaneously. It requires multiple and divergent actions in the mathematical world, in the social world, and the distinction between them is not very helpful. So this is my main point here today.